Observational, the roof of a modern data center is dominated by the physical requirements of cooling. Massive industrial HVAC units and exhaust fans often take up as much space as the server racks they protect. The mathematical models powering modern AI require a nearly exponential increase in power. These localized clusters are now draining terrestrial electrical grids faster than new energy infrastructure can be built to support them. To bypass these earthly bottlenecks, technology companies are looking toward the upper atmosphere. Shifting compute infrastructure into low Earth orbit offers the promise of uninterrupted solar power and freedom from terrestrial land use restrictions. Google's Project Suncatcher plans to deploy machine learning units in sun-synchronous orbits by 2027. SpaceX has gone further, filing for a constellation of up to 1 million satellites designed to function as a distributed orbital data center. SpaceX explicitly frames this ambition as a step toward becoming a Kardashev Type 2 civilization. This project represents a shift in the AI race from terrestrial logistics to the engineering of orbital megastructures. Intuitively, outer space seems like the ideal environment to cool an overheating supercomputer. With ambient background temperatures near 2.7 Kelvin, the vacuum appears to be a natural freezer. In the absence of surrounding matter, a vacuum serves as a near-perfect thermal insulator. Operating hardware in orbit is mechanically similar to placing it inside a sealed thermos flask. On Earth, server farms rely on convection. They move massive volumes of air or chilled liquid past hot components to physically carry heat away. In the vacuum of space, there is no surrounding fluid medium to facilitate this transfer. By moving their hardware into orbit, these corporations have isolated their most power-hungry processors inside an inescapable thermal trap. Thermal radiation is the only mechanism available to reject heat in a vacuum. The efficiency of this process is strictly governed by the Stefan-Boltzmann law. To stay operational, heat must leave this 1U rack as infrared waves, requiring vast surface area. Applied to modern AI hardware, the scale is staggering. A single rack needs a solar array and radiator the size of a soccer field just to prevent melting. This ratio makes gigawatt-scale monolithic data centers physically impossible in orbit. The architecture must be broken down into massive modular constellations to manage the heat. The non-negotiable laws of thermodynamics form the ultimate boundary for this industrial expansion. These physical constraints dictate the financial reality of launching and maintaining silicon in a vacuum. Data models show that while a high-performance AI node costs roughly $1 million to install on Earth, its orbital equivalent costs over $60 million. Hardware attrition presents a further complication. AI accelerators frequently fail when run at full capacity. On Earth, technicians can swap a failed unit in minutes, but orbital hardware is currently unrepairable. Every hardware failure turns an expensive orbital asset into a piece of useless space junk, slowly degrading the constellation's total capacity. Aerospace history contains several warnings about the gap between technical achievement and commercial viability. In 1999, the Iridium satellite constellation resulted in a massive bankruptcy, despite being a triumph of engineering. Motorola built a global network that functioned perfectly, but failed to compete with the rapid cost plummeting of terrestrial cellular infrastructure. A much older project, 1961's Westford, launched hundreds of millions of tiny copper needles into orbit to create an artificial ionosphere. Decades later, clumps of those needles are still tracked as orbital debris. Today's plans involve launching millions of toxic, heavy AI servers. If these massive constellations fail or become obsolete, they risk creating a permanent catastrophic debris field. The precedents of Iridium and Westford suggest that the current rush for orbital AI may be creating a legacy of orbital clutter that lasts for generations. Engineers are developing specialized workarounds to manage the thermal limits of the vacuum. One concept is the liquid droplet radiator. This system sprays a microscopic mist of chilled fluid directly into the vacuum to radiate heat, before magnetically recollecting the droplets back into the ship. Other designs, like tile architecture, move away from traditional racks. These flat, high-surface area compute slabs use their entire external geometry as a passive heap scatter. These systems require a total mutation of computer architecture, driven by the absolute necessity of surviving the orbital environment. While these workarounds function in simulations, the vacuum of space remains an uncompromising environment for high-density electronics. Thermal management serves as the primary constraint on the scale of any computational megastructure. Success in space engineering requires total mathematical submission to the laws of thermodynamics. The deployment of AI into orbit is a collision between industrial ambition and the unyielding realities of the Stefan-Boltzmann law. To see how a flawless engineering project can still end in total commercial failure,